A function f of x sub 1 through x sub n is called homogeneous if when every argument is multiplied by the same positive number lambda, the whole function simply gets multiplied by a power of lambda. In symbols, f of lambda x sub 1 comma lambda x sub 2 comma dot 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 comma lambda x sub n equals lambda to the k times f of x sub 1 comma x sub 2 comma dot 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 comma x sub n. The exponent k is called the degree of homogeneity, or simply the degree of the function. Think of a recipe for a cake. If you double the amount of every ingredient, flour, sugar, eggs, and so on, you get a cake that is twice as big. The size of the cake scales with lambda to the 1, so the recipe is a homogeneous function of degree 1. If you double the dimensions of a solid, length, width, height, the volume grows by lambda cubed, so the volume function is homogeneous of degree 3. The definition works for any number of variables and any real or even complex degree k. K may be an integer, a fraction, or even a negative number, for example, inverse square law. Let f colon script r superscript n arrow script r be a differentiable function that is homogeneous of degree k. Euler's theorem, also called Euler's homogeneous function theorem, states that the first-order partial derivatives of f satisfy a simple linear relation. X sub 1 partial f with respect to x sub 1 plus x sub 2 partial f with respect to x sub 2 plus x sub n partial f with respect to x sub n equals k f of x sub 1, x sub 2, x sub n. In compact notation, the sum from I equals 1 to n of x sub I f sub x I equals kf. The theorem tells us that the weighted sum of the slopes of the function in each coordinate direction reproduces the original function multiplied by its degree. This is a direct consequence of the scaling property, and it works for any smooth homogeneous function, regardless of whether k is an integer or not. Start from the scaling relation that defines homogeneity. F of lambda x sub 1, lambda x sub 2 dot dot dot, lambda x sub n equals lambda to the k power times f of x sub 1, x sub 2 dot 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 x sub n with lambda greater than 0. Treat lambda as a variable and differentiate both sides with respect to lambda, using the chain rule on the left-hand side. d over d lambda of f of lambda x equals sum from I equals 1 to n of partial f with respect to lambda x sub I times d over d lambda of lambda x sub I, which equals sum from I equals 1 to n of x sub I times partial f with respect to lambda x sub I. The right-hand side differentiates easily. d over d lambda of lambda to the k power times f of x equals k times lambda to the k minus 1 power times f of x. Now set lambda equals 1, the equality holds for every lambda, so we are free to pick lambda equals 1. Sum from I equals 1 to n of x sub I times partial f with respect to x sub I equals kf of x. The derivatives on the left are evaluated at the original point, x sub 1 through x sub n, because when lambda equals 1, lambda x sub I equals x sub I. This completes the proof. The key steps are I, using the definition of homogeneity, Roman 2, applying the chain rule, and Roman 3, evaluating at lambda equals 1. Consider the simple two-variable function f of x comma y equals x cubed y squared. Check homogeneity. Replace x comma y by lambda x comma lambda y f of lambda x comma lambda y equals lambda x cubed lambda y squared equals lambda to the 5th times x cubed y squared equals lambda to the 5th f of x comma y. Hence the function is homogeneous of degree k equals 5. Partial derivatives. F sub x equals 3x squared y squared, f sub y equals 2x cubed y. Euler's relation. X times f sub x plus y times f sub y equals x times 3x squared y squared plus y times 2x cubed y equals 3x cubed y squared plus 2x cubed y squared equals 5x cubed y squared equals 5f of x comma y. The left-hand side reproduces 5f, confirming Euler's theorem. Real-world analogy. Think of a rectangular block whose length is proportional to x and width to y, while its height is proportional to x squared y. If you scale the whole block by lambda, the volume scales by lambda to the 5th. 5 independent linear dimensions are being multiplied together. Similar examples. F of x comma y equals x squared plus y squared, degree k equals 2. F of x comma y equals x over y, degree k equals 0 because scaling cancels out, and so on. Explanation. When an exam asks for the degree of homogeneity, the usual trick is to apply the scaling test. Example 1. Find the degree of g of x, y, z equals x squared y over z cubed. Replace each variable by lambda times itself. G of lambda x, lambda y, lambda z equals lambda x squared times lambda y divided by lambda z cubed, which simplifies to lambda cubed x squared y over lambda cubed z cubed, which equals lambda to the 0 times g of x, y, z. So the degree is k equals 0, the function is scale invariant. Example 2, h of u v equals the square root of u squared plus v squared. Scaling gives h of lambda u, lambda v equals the square root of lambda u squared plus lambda v squared, which equals the square root of lambda squared times u squared plus v squared, which equals lambda times the square root of u squared plus v squared, which equals lambda h of uv. Hence k equals 1, the Euclidean norm is homogeneous of degree 1. In an exam, you can quickly write a table. Write the original expression. Substitute x sub I arrow lambda x sub I. Simplify and factor out the overall power of lambda. The exponent of lambda is the degree k. This systematic approach works for polynomials, rational functions, roots, logarithms if they appear inside a homogeneous combination, etc. Euler's theorem gives a handy linear relation among the first-order partial derivatives. For a function homogeneous of degree k, we have x f sub x plus y f sub y equals kf. Why it is useful? Checking work after computing partial derivatives, you can verify the relation. If it fails, you likely made an algebraic slip. Eliminating a derivative, sometimes a problem supplies only f sub x or f sub y. Using the relation, you can solve for the missing one. Integrating factors in thermodynamics, many state equations, for example internal energy U of S and V, are homogeneous. Euler's relation produces the familiar formulas like U equals Ts minus PV plus mu n. Illustration, let f of x comma y equals x squared y cubed k equals 5. Compute f sub x equals 2xy cubed. Using Euler's theorem, y f sub y equals kf minus x f sub x equals 5x squared y cubed minus x times 2xy cubed equals 5x squared y cubed minus 2x squared y cubed equals 3x squared y cubed. Hence f sub y equals 3x squared y squared, which matches the direct differentiation. The relation saved us a step of differentiating with respect to y. The same idea extends to n variables. Sum from I equals 1 to n of x sub I f sub x sub I equals kf. A homogeneous partial differential equation, or PDE, is one where every term has the same total degree in the independent variables and the unknown function or its derivatives. Euler's theorem allows us to reduce such PDEs to ordinary differential equations, ODEs, by using a suitable change of variables. Typical example, find the general solution of x times partial u with respect to x plus y times partial u with respect to y equals u. The left side is exactly the Euler operator for the function u of x and y. The right side is ku with k equals 1. Therefore, the PDE tells us that u is homogeneous of degree 1. We can therefore write u as u of xy equals x times phi of y over x. Any homogeneous function of degree 1 can be expressed as x times a function of the ratio y over x. Substituting this form back into the PDE confirms the choice and leaves phi arbitrary. So the general solution is u of xy equals x times f of y over x, where f is an arbitrary differentiable function. Another case, the Euler-Cauchy ordinary differential equation. X squared y double prime plus a xy prime plus by equals 0 can be derived from a homogeneous PDE in two variables and solved by assuming a power law trial solution y equals x to the m. The underlying idea is always the same. The scaling property reduces the number of independent variables. In engineering, such PDEs appear in fluid flow, potential flow around a cone, heat conduction in self-similar profiles, and in economics, homogeneous production functions. Euler's theorem is the bridge that turns the scaling symmetry into a solvable ordinary differential equation. Q1 B.Tech 2018, Part A. Show that the function f of x comma y equals fraction of x squared plus y squared over square root of x squared plus y squared is homogeneous and find its degree. Answer 1. Simplify f equals square root of x squared plus y squared. Scale f of lambda x comma lambda y equals square root of open parenthesis lambda x close parenthesis squared plus open parenthesis lambda y close parenthesis squared equals lambda times square root of x squared plus y squared equals lambda f of x comma y. Thus the function is homogeneous of degree k equals 1. Q2 M.Tech 2019 Section 2. If g of x comma y comma z equals x squared y cubed z to the minus 1 is homogeneous, write down the Euler relation and compute x g sub x plus y g sub y plus z g sub z. Scaling gives g of lambda x comma lambda y comma lambda z equals lambda to the power 2 plus 3 minus 1 times g equals lambda to the fourth times g. Therefore k equals 4. Euler's relation, xg sub x plus yg sub y plus zg sub z equals 4g. Compute the partials. G sub x equals 2xy cubed z to the minus 1, g sub y equals 3x squared y squared z to the minus 1, g sub z equals negative x squared y cubed z to the minus 2. Hence xg sub x plus yg sub y plus zg sub z equals 2x squared y cubed z to the minus 1 plus 3x squared y cubed z to the minus 1 minus x squared y cubed z to the minus 1 equals 4x squared y cubed z to the minus 1 equals 4g, confirming the theorem. Q3 B.E 2020 short answer. Solve the partial differential equation xu sub x plus yu sub y equals 2u using Euler's theorem. The operator on the left is Euler's operator, so the PDA states that u is homogeneous of degree 2. Therefore u of x comma y equals x squared times f of y divided by x, where f is an arbitrary function. Substituting back shows any such form satisfies the PDE, giving the general solution. These examples illustrate how a short systematic use of the scaling definition and Euler's relation leads to quick exam-ready answers.